Okay, we are on X.2, inferences from tables. I don't really have a lot of notes for this one. Honestly, I think the notes for this, I would say, are the exact same as X.1, which went over the function analysis questions about, what does it mean when the derivative is positive? What does it mean when the second derivative is negative, and so on. Like that is really what is being tested here. And the way that these are tested are in tables. These are very common kinds of multiple choice questions on the AP test. You'll often be given like a table and being asked to analyze it. So being very comfortable with tables and what's going on is really, really helpful for you. Let's take a look at a problem. Given selected values of the twice differential function f, which of the following choices could possibly be true on the entire domain from 1 to 7? So something that I think is something that might be helpful to you in general when you get a table is to visualize it. And to visualize it, you need to draw it. And you don't have to do this, but it might be helpful. So if we think about this, at 1 we're at negative 17. At 3 we're at negative 14. At 5 we're at negative 9. And at 7 we are at negative 2. Right? So something like this. And so you just see what's going on. So you can see very clearly from this that what's happened. Well, the function is increasing the entire time. So which could possibly be true. Well, this could not be true because it's increasing the entire time. So there's no way that the derivative could be negative the entire interval, right? That could not be true for the entire domain. So that's out. So I can immediately eliminate A and D. Well, how about B and C? Well, it is increasing. The next question is about concavity. Is it concave down or is it concave up? If it's concave down, that means my slopes are getting more negative, right? My slopes are getting, think about concave down, right? It's like this, or is it concave up like this? So the question is, am I moving in this part of the curve on concave down, or am I moving in this part of the curve, which is concave up? The way that you do that is by looking at the slopes between each interval. So here, if we look at the slope between here, I went up 3 over 2. You see that I went from 17 to 14, that's up 3, and I went over 2, that's 3 halves. And then from here to here, I went up 5 over 2. So that's 5 halves. And then up here, I went um, over 2 and up 7, so that's 7 halves. So see what's happening? It's getting steeper. My average rates of change are getting steeper. Right? I'm getting the average rate of change between each interval. So even I kind of drew it not quite correctly. Like the way I drew it wasn't really to scale. It looks like it's going to be concave down. It's not. It's concave up because the slopes are increasing. So is that clear? I know it could be increasing because all my values are going up, so I know that this could be true, and I know that it could be concave up because all my slopes are getting steeper, more positive. Okay, let's look at 76. Selected values of twice differential function f are shown below. It tells me that the slope is less than 3 and that the second derivative is negative for all the x in this interval. Which of the following values could potentially be the value of a? So my slope is always less than 3. I should never have a slope greater than 3. And I should always be concave down, meaning that these intervals should always be getting, my average rates of change should always be getting more negative. So if we look at this, let's just kind of see what's going on here. Again, you could graph it to see what's going on. So 11, I'm at 9. At 8, I'm at 21. At 5, I'm at 21. And at 2, I'm at something. So if I'm concave down the entire time, like I should be making this kind of shape here, right? I should be making this kind of shape if I'm concave down the entire time, right? So being very familiar that when you see this, that means concave down, and you can draw that shape and you understand what that means. That's key. You got to be able to do that, right? Um, so let's see here. Well, 25 doesn't make sense because if I put 25 up, 25 is going to be way up here, and that's actually going to like that's not concave down, right? Because my slope from here the slope would have to be concave up for it to make this slope here. See? So there's no way 25 can be it because that ruins my concave down, right? How about 16? 16 maybe, right? So 16 does kind of fit in with our little um, with um, our curve, right, it's going to stay concave down. The question then is, okay, well, surely this has some relevance, and it does have relevance. My slope can never be 3 or more. It can never be 3 or more. It always has to be below 3. So I need to make sure and check that this slope, this average rate of change between 2 and 5 is not going to exceed 3 when I plug in 16. All right, so what I'm doing, I'm getting the average rate of change. I'm going to do 21 minus 16 over 5 minus 2. 21 minus 16 is 5. It's looking fine, guys. It's going to be fine. 5 over 3. Yeah, it's staying below 3, right? 5 over 3 is below 3. So it looks good to go. I would say that only one is true, right? Because it remains concave down the entire time, right? And uh, it it doesn't lead to a derivative does not have to exceed 3 for that to be true. Okay. Last one, given selected values of the function of the trisecond function f with the second derivative less than 0, write a single number that could possibly equal the value of the derivative of 4. Again, this is basically assessing you on your knowledge of the symbols. Like, do you understand what the second derivative being less than 0 means? Like, do you get what that means? Well, you don't. Do you understand that means it must be concave down like this? Okay. Do you understand that means that the slopes must be decreasing each time? So um, the way that we do this is you're gonna like the same way that we were kind of doing it in other ones. You got to check the average rates of change between each of these intervals to see what's going on. So if we look at the average rate of change here, we're going up 2 over 1. So this is a slope of 2. Between these two, I went up. We went up 0.75 and down and over 3. Right, I'm doing the calculator. What is that? I mean, it's 0.25. No, I don't need to do the calculator. That's a quarter. That's my slope. Here I went over a quarter over 1. Okay, so that's also 0.25. Okay, I don't know if that's like a misprint on their part, or if I'm missing something. I don't think I'm missing anything though. Really, that shouldn't be like that should not be also 1/4, but it. Oh no, my bad, guys. It's going down. Sorry, it's negative 1/2. See, sorry, 1.75 to 0.25. It's I don't sorry, I don't know what I was thinking there. It went down a half. So no, it is all good. It is always concave down, right? It went from 2 to 1/4 to negative 1/2. The slope is constantly decreasing. So what could be the slope of 4? The slope of 4 could basically be any number between 2 and 1/4, because the slope of 4 must be less than the slope um, between 3 and 4, right? And it must be larger than the slope between 4 and 7. So any number between 1/4 and 2 is going to work, because it's going to show that it is decreasing because it's going to be less than 2, but it's still possible because it's greater than 1/4, right? So maybe I'd say like 1 or 1/2 or 3/4, and any of these would work, right? So f(4) could be any number uh, greater than 1/4 but less than 2. So any number in that range would work for this answer. And that's it. So these ones, guys, these are important. I think they really help you build your mastery of first and second derivative. Um, these are great.